Suppose we have training data which are pairs. Training data pairs x, y. And so y has a distribution conditional on x. And also, so conditional on x and defined by parameter theta. Y follows a distribution f that depends on x and theta. Every y has a different distribution because every x can be different. But what all these distributions have in common is the same values for the parameters theta. We have a conditional probability so probability of y equals y given x equals x and theta. So for any particular observation little x, then for every possible value of little y, there's going to be a conditional probability of that little y given little x. If this is my model, so these are the probability distributions that I'm assuming, the family of probability distributions. Do I have any model of the probability distribution of x? So for each x, I have a model for the probability distribution of y given x. But do I have any model of the probability distribution of x? No. Okay. Yeah, so the answer is no. I've given you, so the way to see it is, if supposing I had probability of x comma y. So x, y is my training data. It's a training example. And then just using the rules of probability, this is the probability of x times the probability of y given x. And I've provided a family of distributions of probability of y given x. But I haven't provided any family of distributions for x, which means that I don't have any model of p of x, I don't have any model of p of x comma y. When is it, there's a principle in machine learning, maybe a slogan, that, don't try to learn anything that you don't need to learn. Don't do any work that you don't need to work. Don't do any work that you don't need to do. And here, I'm going to learn some model for p of y given x, but I'm not going to learn a model of p of x. When's it reasonable to learn a model of p of y given x, but not learn a model of p of x? There. And people understand the question? Yeah. Why would you not want to learn a model of p of x?
Your x's are just given or fixed.
Your x's are always going to be just provided to you. So typically, if you're doing supervised learning, your training data is x, y pairs. You have an example x, and then you have its label y. And then your training, and then for test data, nobody tells you the label y. If they told you the label y, you wouldn't need a classifier. You wouldn't need to do any learning. But for test data, they do tell you the x. And if they're going to tell you the x at test time, as well as at training time, then why bother learning anything about the x's? So, yeah.
Isn't learning X precisely what like language modeling classifiers are trying to do?
Well, I think the short answer to your question is yes. And so let me try and explain that a little bit. So imagine that. So we're talking about supervised learning. So you think of X as being the input and Y as being the output. And so your input X might be an English sentence, and your output Y might be a French sentence. And actually, okay, let me try. Scenario. So X equals English sentence. Y equals French sentence. And then you have training. You have XY pairs. And then for test, you have X given, Y unknown. And you need a function, probability of Y given X. And then in principle, you could do translation by choosing the, so output Y hat is argmax P of Y given X. So now what's a language model? I think a language model is I guess technically it's probably a mass function that P of Y. And so if Y is French sentences, then this would be a probability function that tells you which French sentences are likely, which would be correct sentences, and then which French sentences are unlikely, that would be incorrect sentences, and they would have low probability. And when you're choosing a Y to be your output, you really want it to satisfy two criteria. You want it to have high probability given the input English sentence, and you also want it to be a good French sentence. So language models are actually used to tell you the probability of the output sentence being a good sentence in the output language. And if I have this formula, so this is just a simple formula of probability theory, and I can also write it as P of Y times P of X given Y. Then actually the statistical approach to machine translation involves building a language model somehow, which is a model of P of Y, and then really building an inverse, what you could call an inverse translation model, which is the probability of the English sentence given the French sentence. And then I guess, and there are reasons why they do it this way rather than doing it this way. And I think, if you did it this way, then you'd be putting all your eggs in one basket. You'd need to learn a very good model of P of Y given X. And if you do it this way, it's a divide and conquer approach to the problem. You can try to make this model good, and you can also separately try to make this model good. But I'm not an expert on statistical language processing, and I'm certainly not and very knowledgeable about machine translation. But it is worth understanding this. So this is the framework for machine translation, and log linear models actually were first developed and applied and found to be really successful in natural language processing. And it's interesting, if you think of statistical natural language processing is an application area for machine learning, but it's one of the few application areas for machine learning that has actually driven the central machine learning technology. There are people in statistical machine translation were doing things in machine learning that were more advanced than what anybody in machine learning was doing. And now there's this back fertilization of ideas, in particular log linear models. Okay. So I was talking about conditional likelihood. So we have a principle of conditional maximum likelihood. So, oops. So given training data, which is x1, y1, up to xn, yn, then select theta hat equals argmax over theta of product from I equals 1 to n of probability of y I given xi and theta. It's very similar to the principle of maximum likelihood, except that instead of maximizing a product of probabilities, we're maximizing a product of conditional probabilities. And so we're taking the xi's as given, and in training data, everything's given. So the xi's are given, the yi's are given, but we want to choose theta so that all these probabilities together are as high as possible. There's in order to justify the principle of maximum likelihood as being a product, I had to assume that my training examples were independent. Do I need to assume that my training examples are independent in order to justify this principle? This is quite an important question, and the answer is quite important. Because the answer really tells you when you can use this principle and when you mustn't use the principle. So you mustn't use the principle of maximum likelihood, at least in the product form, when your training examples are not independent.
Well, in this case, the outcomes are assumed to be independent.
Yes. So this principle is actually more broadly applicable, because I don't need to assume anything about the x's being independent. All I really need to assume is that the y's are independent. And I think as a special case of the y's being independent, if each y only depends on its corresponding x, then I don't need to assume, then that's enough. So this is justified given all yi are independent, and so it's enough to assume each yi depends only on the corresponding xi. So this is this is actually the framework that is used in much of traditional statistics, and in particular, it's the framework that's used for linear regression. So in linear regression model, is that y equals, you have some intercept, and then you have a parameter vector beta bar times x bar plus you have some Gaussian which has 0 mean and variance sigma squared. So this is the standard linear regression model. And and in this model, each y depends on the corresponding x's. But and so that makes the y's conditionally independent. That makes the y's independent if the x's are known. And so then that makes it justified to choose the parameters alpha and beta even if the x's are not independent. And here's an illustration of that. Okay. Yeah. So,
you could test your data set X and Y to make sure that this is actually true then.
You could certainly conceptually you could test your
The training set.
Well, and conceptually you could test the training set and the test set to see whether the x's have the same distribution in both. Let me draw a little picture which will think. Okay. So supposing that these are my training points. And then this is my linear regression line. So linear regression, training points, and then supposing that these are my test points. So clearly these test x's don't have the same distribution as these training x's. And so conventional machine learning would say you can't learn from these training points and then make predictions for these test points because your training set and your test set come from different distributions. But what statistics says is we don't need to assume that the x's come from the same distribution. We just need to assume that the y's follow the same model and that each y only depends on its corresponding x. And then that'll justify the principle of maximum conditional likelihood for learning the parameters of the model, and then it'll be justified to apply the model to the test points. This is quite an important point, and sometimes this is what's going on here is called covariate shift. So covariate means features, means predictors, and covariate shift means that in your test set, the input examples have a different distribution from in your training set. But as long as, and so if you built a model of the x's, like maybe here's a Gaussian model for the x's, obviously that model is not going to be correct for your test points. But if you have a conditional model of y as a function of x, then that conditional model is going to be justified by the principle of conditional maximum likelihood. So this gives you a much wider range of possible learning tasks you can attack now, because you don't need your test x's to be from the same distribution as your training x's. And so this property of being robust to covariate shift is going to apply to logistic regression. It's also going to apply to log linear models and conditional random fields. Okay. So I think we're supposed to take a break in 5 minutes. So I'll put up the equation for logistic regression. And logistic regression is a special case of log linear models. And conditional random fields are a another special case of log linear models. The model is the probability of y given x, and we have parameters alpha and beta. It's 1 over 1 plus e to the minus alpha plus sum from j equals 1 to d of beta j xj. So x belongs to d-dimensional Euclidean space. Y is binary. So y is really a coin flip. So in the Bernoulli example, every coin flip was assumed to have the same distribution. And here, I also have coin flips. It's just that the probability of success for each coin flip depends on some observations x. Each example x could be a different coin, and each coin has got some measurements. What metal it's made out of, what its mass is, whether it's dented, and anything else you want to measure about the coin, and that will go into your x's. And then you want to have a model of the probability that this coin is going to come up heads, and this model is going to have this mathematical form. And this model is called logistic regression. It's a binary classifier. So a binary classifier is a function that you give it an input, an example description, and it gives you output a predicted label, like survives, doesn't survive. And what this actually gives you as output is the probability of survival. So if you took that probability and you thresholded it at 0.5, you could get an actual binary prediction. But by telling you the probability of survival, it's giving you more information than just giving you a yes/no prediction. Okay. So let me just write this in a slightly different way. So I'm going to call this P. So P is just a notational shorthand for this. And now log P is minus log of 1 plus e to the minus alpha plus the sum beta j xj. And then okay, so P over 1 minus P is so actually what I need is just 1 minus P is so it's the numerator minus the denominator. It's the denominator minus the numerator over the denominator. So it's e to the minus, and then this thing in parentheses, over 1 plus e to the minus this thing in parentheses. So P over 1 minus P is 1 over e to the minus the thing in parentheses, and then log of P over 1 minus P is minus the thing in parentheses. And actually that's plus. Okay. I think it's 12:30, so we'll stop for a break. And when we come back at 1:30, I'm going to analyze logistic regression, provide a training algorithm for logistic regression. The training algorithm is going to be stochastic gradient descent. And so it's going to be the simplest version of the training algorithm for log linear models in conditional random fields. So it seems that our attendance is 5. Am I going too quickly, too slowly? Is too boring, too basic, too what?
Good for me.
Good? Okay, good.
I'll speak up, I'll say.
Okay. So if you're not planning to come back at 1:30, then speak up and say why. Get started for our second session. I see a couple of people who, one person who wasn't here for the first session. So I just want to explain that we have a very small audience, and I'm doing this like I do my graduate classes. So I really want to go slowly and hope that you understand things, and questions are very welcome. And this is not going to be any sort of fly-through of PowerPoints. I did, at the beginning of the first session, I did ask the people who were here to introduce themselves so I could find out what their interests were. So if you don't mind, I think, can you tell us who you are and what you're interested in?
Oh yeah, my name is Johnny Yi, and I work for Yahoo Search.
Uh-huh.
I'm mostly interested in actually query processing and query understanding.
Uh-huh.
So, and a lot of machine learning mechanisms are with
Yeah.
percent of success on the content side.
Mhm.
But when we try to apply the same kind of technology on the query for queries, we get much less quality of result.
Uh-huh.
Mostly because we don't have as many context as the content when we look at only the queries.
Uh-huh.
So I try to understand some other or learn some other techniques which might work better
Yeah.
with much amount of context that we can use to train the model. So I don't know if this will be easier, better, helpful or not, but
Yeah.
this is
So you're interested in the analysis of queries that users send to search engines? Yes. I actually think that what I'm going to be talking about is, well, it would be a research question to figure out how it's applicable to search engine queries, because conditional random fields are fundamentally models where, for supervised learning, you give them an input, and then for training data you have an output, and then you learn the relationship between the input and output, and then you can use this for test data. So the input might be an English sentence, the output might be the labeling of that sentence in terms of part of speech, noun, verb, pronoun, adjective, and so on. But you need labeled training data, and then what makes that difficult, one of the things that makes labeling sentences with part of speech difficult is that the sentences are long and queries are short. You don't naturally have queries with labels for training data that you don't have for test data. So I don't think that what I'm going to be talking about is going to be directly applicable to queries. But conditional random fields are certainly applicable to the analysis of natural language for tasks like information extraction. And so with some creativity, they may well have some benefits for helping to improve the performance of search engines. But, okay, I'm going to continue where I left off with logistic regression. And so we're talking about the probability of a label y, and then this label y is conditioned on the input x, and then we have the parameters alpha and beta. And the model is that the logarithm of p over 1 minus p is linear. So it's alpha plus sum over j beta j x j. And some useful terminology. So P is the probability of the event Y, and it's probably a Y equals 1. And then P over 1 minus P is called the odds. And log P of 1 minus P is called the log odds. So this model says that the log odds is a linear function. And this is a reasonable function because probabilities are bounded between 0 and 1. And so odds then are going to take a value between 0 and positive infinity. And then log odds take values between negative infinity and plus infinity. And that's the possible range of values of a linear function. And so it wouldn't be mathematically coherent to make the probability be a linear function of the data. And so linear functions are the simplest sort of functions. So if we want simplicity, we want a linear function. But then in order to map the range from negative infinity to plus infinity to the range 0 to 1, then the log odds, or the inverse transformation of log odds, is the simplest way of doing that. So this is really the justification for the form of the logistic regression model, that it's linear, which is the simplest possible, and then with a transformation. Something, and this, if you have here the log odds, and this is the 0 point, and then here you have the probability, which ranges from 1 to 0, then a log odds of 0 corresponds to a probability of 0.5. So 0.5 divided by 0.5 is 1, log of 1 is 0. And this function, so I didn't draw it there, but it's a sigmoid shape. It's a long stretched out S shape. And it is a monotonic. So P is a monotonic function of log odds, and log odds is a monotonic function of P. And so the bigger the value of this linear function, the bigger the probability. And so that makes these coefficients interpretable. So so xj is a feature of x. We're thinking of x bar as being a vector of feature values. Remember, so this is sum from j equals 1 to d, and we have x bar is in r to the d. And there's a very common special case for the features xj, which is that they're binary. So if xj equals 0, xj equals 1, then that's a special case of xj being a real number. And so if xj is real valued and beta j is positive, then this parameter is saying that everything else being equal, a bigger value for xj makes y equal 1 more likely. And if xj is binary, then, and beta j is positive, then beta j is really the bump up in the log odds that you get from having the value, the feature xj equals 1 instead of the feature xj equals 0. And the notice that if you're evaluating this linear function and you have an xj which is 0, then you don't even need to do any multiplication, because you just get something times 0 is 0. And so evaluating this is going to be very fast if xj is sparse. And this is the common situation. So, the x bar might be a vector representation of a document, and then the y might be the label, is this document relevant or not relevant? And if you represent a document as a vector of how many times each word in your dictionary appears in a document, as I mentioned before, you might have 60,000 words in your dictionary, so x bar is a vector of length 60,000. But if you have a document that only has 200 words in it, then at most 200 of those xj are going to be non-zero. And then you can evaluate this model just by looking at the non-zero xj. So this is a model which is sort of, it has a good match to the very common situation in learning where you have a very large number of features, but most of those features are switched off for most examples. Okay. So this logistic regression model has several other advantages, and those advantages carry over to log linear models. So first advantage is that correlated features don't lead to problems. So you can make any feature you want be xj, and then the model is going to learn the coefficients. If you train with maximum likelihood, you're going to learn the coefficients that give you the best estimate of the probabilities, and you're going to get the best possible model even if features are not independent. So in fact, we don't need the training examples, we don't need the x's to be independent, we don't need the features to be independent, which really means we can just throw in the kitchen sink of examples and throw in the kitchen sink of features. And this is in sharp contrast to naive Bayes in particular. So if you're learning a naive Bayes classifier, then, and you have features that are correlated, then your classifier is going to be reduced in accuracy. Okay, and so second major advantage is that you get numerical scores. So if you're learning a decision tree, then at least a simple version of a decision tree, you have a test example and you start at the root of the decision tree and you navigate down to the leaf of the decision tree, and then at that leaf you get a prediction. But that prediction is going to be a yes-no prediction. And so if you have two different examples and you predict positive for both of them, the decision tree doesn't tell you which example is more likely to be positive. It doesn't give you any confidence values for your predictions. But other classifiers, like support vector machines, for each x, it'll give you a numerical score, and then the bigger the numerical score, the more likely that example is to be positive. So if you have a classifier that gives numerical scores, you can use it to rank examples. So maybe your classifier is telling you which web pages are relevant to a query. And you can take the top 10 web pages that have the highest score and produce those as your output if that's what you're interested in. So it's very useful to be able to get rankings as the output of a classifier. And so numerical scores, so that means that SVMs are better than decision trees on this measure. But there's something that's even better than numerical scores as the output of a classifier. Anybody? Sorry?
It is the probabilities that you want.
Probabilities that add up to 1?
No, I mean the output ranges from 0 to 1.
So yeah, so here, with this model, with logistic regression, the numerical scores range from 0 to 1. And so you can use them for ranking. But support vector machines give you numerical scores that actually can range from negative infinity to plus infinity. So that's a small difference. But you can also use the numerical scores you get from a support vector machine for ranking. But now the question that I'm asking is, what's even better than numerical scores? So numerical scores let you solve problems that discrete predictions that you can't solve with discrete predictions. But there's something that lets you solve problems that you can't solve with numerical scores. Well, the critical thing about probabilities is not that they arrange between 0 and 1. It's that they actually have a genuine frequentist meaning, a genuine meaning. So what I'm going to say here is meaningful probabilities. Yeah. So a naive Bayes classifier will give you scores between 0 and 1. And so they look like probabilities, but they're not really meaningful. And I could go into a digression about naive Bayes, but the basic fact about naive Bayes is that the numerical scores you get out of it are almost always they're almost always excessively extreme, either too close to 0 or too close to 1. And they're not honest probabilities. So meaningful probabilities, and the word that's often used is well calibrated. And I'm not actually going to put up a definition of well calibrated. I think it's actually a rather difficult philosophical issue. What is the definition of well calibrated? I think it's a concept that is that's pretty easy to understand intuitively, but hard to pin down. And the reason why it's hard to pin down is the same reason why it's hard to define what you mean when you talk about the probability of a one-off event. So, the obvious example is the US presidential election. And, right now, it's uncertain who's going to win. But one of the candidates looks much more likely to win than the other one. And so, you can say that the probability that Obama will win is 0.85. But what does that really mean? If there were 100 elections and he won 85 times and McCain won 15 times, then it's obvious, then it's clear that the probability is 0.85 that he'll win. It's clear what the meaning is, and then it's clear that that's a correct probability. But if there's only one election and he either wins or he doesn't win, then what's the meaning of the probability being 0.85? And so that's why I'm not going to try to define what well calibrated means. But I will say that, so let x1 to xn be test examples with predicted probabilities. So probability of y equals 1 given xi equals vi. So S be the sum over I of vi. And let T be the actual number of y equals 1 cases in the set 1 to n. So we have 100 test examples. We make a prediction vi for each of those test examples, and then we add up all those predicted probabilities, and then later on we get to find out the truth about the test examples, and we discover that among these n test examples, T was the actual number of positives. So what can we say about the relationship between S and T if the probabilities are well calibrated? Should be equal plus or minus random noise. So the expected value of T is S. This is something that you can only say if the probabilities are well calibrated. And so this is a big advantage of having well calibrated examples. And there's a scenario that I think illustrates this very well. So, airlines always overbook flights. And, but they need to make a decision of how much to overbook the flight. If there are 100 seats on the plane, should you sell 110 tickets or should you sell 120 tickets? And so in order to make that decision, they really need to estimate for each flight how many people are going to be no-shows. So one way to do that is, and of course they have lots of training data about millions of past passengers, and for each past passenger they know whether that person was a no-show. And they know various characteristics of these passengers. In particular, they know behavioral characteristics like, did the passenger buy his ticket the same day, the previous week, the previous month, more than a month earlier, and so on. And so what they can do is build a classifier. They can train a classifier to try and predict for each person, for each flight, is this person going to be a no-show? And I'm sure they could train decision trees and get some reasonable accuracy. That, if it's a business person and they bought their ticket a day before, then they're more likely to be a no-show. And if they bought their ticket 1 hour before, then they're less likely to be a no-show. So you could come up with pretty good predictions about who's going to be a no-show. But the airline doesn't really care about that. They don't really care about who are the no-shows, they just care about how many no-shows there are. And so this is the number they really care about. And then this is the estimate they would like to get. So what they really want to do is run their predictive model on every passenger who's booked on the plane, and then just add up the probability of them being no-shows, and that's the estimate of the total number of no-shows, which is what really matters. And but they can only do this if the classifier is giving well-calibrated probabilities. You can't add up the numerical scores you get from a support vector machine and get an estimate of the number of no-shows. Yeah?
Can we calibrate the SVM output by taking the log of P over 1 minus P equals to the
Okay.
output of SVM?
Yeah. So there is a fair amount of research on how to convert the output of an SVM classifier into being a well-calibrated probability. And the most widely used method is to take the output of the SVM, use it as really a single feature, so represent each example by just one feature, which is its SVM output, and then train a one-dimensional logistic regression on top of that. And that works quite well in practice.
Because if we are using linear SVM, the format is very similar to the logistic regression. It's just the summation.
Yes. Yes. So linear SVMs are very closely related to logistic regression. In fact, they use the same sort of linear transformation of the input examples, but then the key difference is that they're actually using a different objective function for training. So for training with logistic regression, we're doing maximum conditional likelihood. Support vector machines are doing maximum something else, which is a loss function that involves a loss function that's called the hinge loss. And so actually, support vector machines are a good illustration of how conditional likelihood and maximum likelihood are not the only possible induction principles. They make a lot of sense, they're widely used, they're very useful, but I had an example with the mixture of two Gaussians that showed that that maximum likelihood has pathologies, and then support vector machines show that there's a reasonable alternative. But support vector machines don't give you well-calibrated probabilities, and so then you can put logistic regression on top of a support vector machine. And that works well in practice. But doing logistic regression directly works well in practice also. I thought there was one more thing I wanted to say on this. Yeah. Oh, yeah. So actually, maybe a fourth advantage of logistic regression is that it handles unbalanced training data. So there are lots of machine learning applications where we have a positive class and a negative class, and one of those classes is very rare and the other class is very common. So, maybe we have credit card applications coming in, and most of those applications are legitimate. A few of those applications are fraudulent. And we might want to train a classifier to try and recognize which applications are fraudulent. And we have the issue that's called unbalanced training data, that one class is much more rare than the others. And logistic regression just has no difficulty with that at all. You'll get a classifier that will predict well-calibrated probabilities of being positive. But supposing that the positive class is very rare, and you've trained your logistic regression classifier, and it's going to give you probabilities of being positive. It's quite possible that for every test example, your predicted probability will be less than 0.5. So what's the real world meaning of having a predicted probability of less than 0.5? Sorry?
It is negative.
I think, so the real world meaning of having a predicted probability less than 0.5 is that if you had to make a commitment about, is this application fraudulent or legitimate, you would say, well, it's legitimate. There's a more than 50% chance that it's legitimate. However, you still have a big difference between an application where you predict the probability of fraud is 10% and an application where you predict the probability of fraud is 0.1%. The 10% one is still much more suspicious than the 0.1% one, but the level of suspicion doesn't reach the 50% level. So if you are making a yes-no prediction and you were using a threshold of 0.5, you would predict that everything was legitimate. But the classifier will still let you rank applications according to how suspicious they are, from less suspicious to more suspicious. And these predicted probabilities, if they're well calibrated, they're going to have the property that they're centered around the base rate. So the base rate is the overall probability of being positive. And some test examples are less probable, some are more probable. And the calibrated probabilities, some of them will be lower than the base rate, some of them will be higher than the base rate. And if the base rate is very low, then it's quite possible that all the predicted probabilities will be below 0.5. But then your classifier is telling you that you have a lot of uncertainty. And notice, probabilities can be well calibrated, but still uninformative. Supposing that supposing that overall 5% of your passengers are no-shows, and for each individual passenger you predict a probability of being a no-show of 0.05. Then you've got predictions that are well calibrated, but uninformative. Yeah. Okay. So that's enough about logistic regression, the model. Now let's look at a training algorithm. Okay, so logistic regression training. And so we're going to so we're going to do gradient ascent. So this is hill climbing along the gradient. So the goal is to maximize the log conditional likelihood. And so the algorithm, this is just a sketch, so start with an initial guess. And remember, the parameters are alpha and beta. And then we're going to compute the gradient of the log conditional likelihood. And then we're going to update the parameters in the direction of the gradient. And the gradient means the multidimensional derivative. So I won't try to draw an illustration in multiple dimensions, but I will illustrate it in one dimension because this is really the pretty much the simplest possible way to do numerical optimization. So maybe here's my parameters. So beta would be a parameter. And here's the function that I'm trying to maximize, which is the log conditional likelihood. And here's an initial guess, say beta naught. And so here's the value of the function at beta naught. And this is not the maximum possible value for the function. So what I do is I compute the gradient. And in this case, it's one-dimensional, so the gradient is just the derivative. And so this is really the slope of the function, the derivative. And here, the slope of the function is positive. And if the slope of the function is positive, what that means is that the function is increasing in this direction and decreasing in this direction. So that tells me that to improve beta, I should move in this direction. So beta 1. So beta 1 is beta 0 plus the d by d beta of the log conditional likelihood. So I times some lambda. So the and so lambda is some constant, which is positive. And then if I multiply it by the derivative, and the derivative is positive, then I'm going to move from beta 0 to beta 1. And if the derivative was negative, I would move to a beta 1 over here. And that would be the case if I was over here, for example. The derivative would be negative, and then the update would take me in this direction. And this updating process, it's the basic idea behind most optimization algorithms, and it's sometimes called hill climbing. It's called gradient ascent if you're looking for a maximum, and gradient descent if you're looking for a minimum. And what are some things that can go wrong with gradient ascent? Just based on looking at this picture, what are some things that can go wrong?
Obviously, you can find a non-global maximum.
So, yes. So, supposing that your function looked like this, then here's the global maximum. Here's a local maximum that's not the global maximum, and gradient ascent could take you to here, and then here the derivative is 0, here the derivative is 0 also, but because the derivative is 0 here, then this update rule is going to tell you to to make no moves. And so so you're going to be stuck at the local maximum. And actually one of the advantages of logistic regression and log linear models, so conditional random fields also, is that it's possible to prove that there are no local maxima. There's only one global maximum. And so hill climbing, so you don't have the problem. You don't have a problem with local minima or local maxima.
What about saddle points?
I think you can have. I'm sure you can. You can have the maximum being non-unique, so it's like having a ridge. But I don't think that you can have. I don't think you can have saddle points. And if you do something called regularization, then I think you can prove that the global maximum is strictly unique, that you don't even have a ridge. Certainly local maxima are not, local maxima don't exist, and you don't have a problem in practice finding a global maximum. Now it's possible that there may be a ridge or something like that. So the local maxima are a possible problem. What's another possible problem? Even when you only have one global maximum, how could this gradient following go wrong?